Hello everybody, this is Dr. Christopher White and welcome back for part 3 of Cenozoic life history. So before we go any further, let's just get the code word out of the way. The code word for this presentation is Oreo. I repeat, Oreo. That's O-R-E-O. One more time, Oreo, like the cookie. So please make sure you write that down and put it somewhere safe because you'll need it for the code word quiz. Alright, so now we're going to be moving on to the Ungulates, which is a group which we otherwise refer to as the Hoofed Animals. So the Ungulates is an informal term referring to several groups of extinct and existing hoofed mammals of the order Artiodactyla and Perissodactyla. Now, the vast majority of these mammals are herbivores, although there are a few examples of omnivorous ungulates during the Cenozoic. Now, the group Artiodactyla is also referred to as the even-toed hoofed mammals, and they are the most numerous with about 170 living species, including groups like cattle, goats, sheep, swine, antelope, deer, giraffes, hippopotami, and camels, to name but a few. Now, the second group, the Perissodactyla, are often referred to as the odd-toed hoofed mammals, and there are only 16 existing species of this particular group, and it includes animals like horses, rhinoceroses, and tapirs. However, during the early Cenozoic, the Perissodactyla were actually more common than the Artiodactyla. Now, if we look over here in the bottom right, you can see a diagram showing you the differences. So over here on the left we have the Perissodactyla, and over here on the right we have the Artiodactyla, and you can see quite clearly in the case of the Perissodactyla they have essentially 1 or 3 toes. In the case of the Artiodactyla you have 2 or 4 toes. So the distribution of weight on the foot varies between the two groups. In the case of the Artiodactyla, the weight is borne by either 2 or 4 toes, with the weight primarily focused on the 3rd and 4th toes in both cases. Now, the 4-toed varieties of Artiodactyla have typically lost their first toe or its vestigial. In the case of the 2-toed varieties, typically the 1st, 2nd and 5th toes have been lost or they are vestigial. In the case of the Perissodactyla, the weight is borne by either 1 or 3 toes, and the weight is primarily borne by the 3rd toe in both cases. Now, the 3-toed varieties of Perissodactyla are typically missing their 1st and 5th toes, while the 1-toed varieties are typically missing the 1st, 2nd, 4th and 5th toes. In most cases, the toes are not vestigial, they've been lost completely, so they're no longer present, although you can sometimes get rare occurrences where you do get animals like horses born with 3 toes rather than the standard 1, but on the whole those are very, very rare occurrences. Now, a significant number of hoofed animals, now this includes the Artiodactyla and the Perissodactyla, use speed in order to escape predators, and the way they've managed to help in this process is to develop long, slender legs which increases their stride length, thereby allowing them to run faster and cover more ground more quickly. Now, this has been achieved by extending the bones of the palm. So if we look over here on this diagram, you can see a generalized skeleton for a horse. And you'll notice that the palm bones, which are marked out here in the darker brown color, which we would normally call the metacarpals, and the bones of the foot, which we would normally refer to as the metatarsals, have been extended in order to allow the leg to be longer. And of course, this longer leg is going to allow for the increased stride length and the aforementioned increase in speed. The fast-running ungulates tend to have fewer bones in their feet when compared to their ancestors, and this is primarily the result of the reduced number of toes. Now, this means the remaining bones will typically have to become more robust because they need to compensate for the fact that they're carrying more weight. So typically you will see the bones become bigger and chunkier. Now, those ungulates which are not built for speed tend to favour 2 other possible methods of avoiding predators. The first is the use of darting movement. So this is quick bursts of speed that will allow the animal to get under cover or to enter a burrow. The other possible option is size, and so, when we think of the larger ungulates, so like the rhinos, the hippos and the camels, you would have to be a bit of a fool to attack those animals because they're just so big. Now, in the case of these larger ungulates, we see that they have feet which are designed for weight support through the development of large bones, and we also see that they tend to have spread toes, and this produces a broad foot which is very good for distributing the animal's weight. Now, both groups, that's the Artiodactyla and the Perissodactyla, are predominantly herbivores, with premolars and molars adapted for chewing vegetation. Now, both groups have undergone a process called molarization, and this is an evolutionary trend through which the premolars have become broader and flattened, so they look like regular molars. Now, this helps to provide an additional set of chewing teeth, and so this means you have a near continuous row of grinding teeth down the side of the mouth, which can be used to pulp vegetation more efficiently, thereby allowing for maximum nutrient extraction. The ungulates are split into two groups based on their eating habits. The first group are the browsers, and this group eats tender leaves, twigs and shoots from trees and shrubs. The second group are the grazers, and this group will primarily eat grass. Now, the thing about eating grass is that along with the grass you will also ingest small quantities of soil, and the problem is that soil contains very small fragments of rock, typically silt and sand sized clasts. Now the problem is obviously these small pieces of rock are going to be abrasive, and so as you're chewing the grass you are also going to be chewing the soil, which contains these small pieces of rock, and they're going to slowly grind down your teeth. Now, if you're a grazer and you were to have a tooth similar to a human-style tooth, which is called a low-crown tooth, you would very quickly be in trouble. So if we look at the diagram down here in the right, you can see a low-crown tooth right here. So we have the portion of the tooth which is going to be above the gum line. You can see that's protected by a hard layer of enamel. Then underneath that we have the dentine, and then of course we have the nerve. Now, low crown teeth are good if you are eating a diet which isn't particularly abrasive. However, if you're a grazer, you are going to be exposed to all these small rock fragments in the soil, and that's going to very quickly degrade the enamel and the dentine down, and so the nerve is going to get exposed very, very quickly. And of course, this is going to cause you great amounts of pain. It's going to inhibit your ability to eat, and eventually it will mean you'll get weaker and die. So what happens with the ungulates is the grazers develop what's referred to as a high-crowned cement-covered tooth, and these are extremely abrasion resistant, and you can see an example over here on the right. So if we look, we can see number one, the distance between the top of the tooth and the nerve has been dramatically increased. So this means there's more material to be worn down, so the tooth is going to last longer. The next thing that we see is that we have the layer of enamel and we have the dentine. So we have these two hard materials which are going to take a while to wear down, but we also have the addition of a cement coat along the outside of the tooth, and this gives you essentially a third layer of protection, making the tooth even more abrasion resistant, so it will last longer. And of course this means your animal will be able to survive for longer. It will have, it won't have dental issues early in its life. So let's spend some time looking at the Artiodactyla. So the earliest Artiodactyla appear in the early Eocene. The oldest example is an antelope-like browser called Diacodexis, and it was about 50 centimeters long, and it's actually quite an interesting animal. So although we classify it as a member of the even-toed ungulates, it actually had 5 toes on each foot. Now the reason we classify it as a member of the Artiodactyla is because we can see the 3rd and 4th toes are already beginning to become overdeveloped, and they're bearing most of the weight. Now this means that given enough time, the 1st, 2nd and 5th toes would have become vestigial and would eventually have been lost. Now we see the Artiodactyla quickly diversifying throughout the Cenozoic, and many of the groups that appear will have lived in North America for at least a period of time. So the first group we're going to look at are the Oreodonts, and this is a group of pig-like grazers who were approximately the size of sheep. Now, they were a very common group until their extinction in the Miocene. This particular group diversified throughout the Oligocene and the Miocene, and eventually they began to occupy habitats ranging from grassland all the way through to semi-aquatic environments, a bit like hippos. Now, when you look at the skeleton, you can see they have these very powerful looking skulls with a very short nose, so they would have had quite pig-like features, and this initially led to them being classified as part of the same family as pigs. However, recent studies have actually shown that they're probably more closely related to camels. Now, we can tell that most of them were grazers because when we look at the skulls, we can see they have high crown cement covered teeth, which of course you want if you're a grazer. The next group we're going to look at are the camels. The camels were common in North America from the Eocene onwards. Initially, camels had a four-toed foot, but this had changed to a two-toed foot by the Oligocene. Now, trends in camel evolution during the Oligocene included an increase in body size, the aforementioned reduction in the number of toes, the fusing of the two toes together to produce a more robust leg and foot, a reduction in the number of front teeth, a shift to high crown teeth, and molarization. Now, these changes are primarily driven by the changes in environment which are occurring in North America during the Eocene-Oligocene boundary. So if you remember, conditions in the Paleocene and the Eocene were such that large amounts of central North America were covered in extensive forests. And of course, if you're a forest-dwelling organism, typically you don't want to get too large, because if you get too big when you're trying to escape from a predator, there's a chance you might get stuck between trees, for instance, and obviously if you get stuck, you get caught. And so having an extremely large body design in a forest is often not an advantageous thing. Another adaptation that we tend to see in forest-dwelling animals is because there are so many trees and bushes about, typically those animals will be browsers rather than grazers. Now, as we move from the Eocene into the Oligocene, we see a change in the environment which causes these extensive forests to die back, and they're replaced by grassland. And so we can see this change when it comes to the adaptations which the camels are showing during the Oligocene. So for one, we see the appearance of high crown teeth and molarization. So obviously the appearance of the high crown teeth is telling us that they are shifting to a grazing diet. So they're starting to eat grass, which means they're ingesting small quantities of soil, so they have to evolve teeth which can deal with this extra abrasion. The molarization is also helpful because grass is actually quite a difficult plant to extract the nutrients from. It's not very nutrient rich and it's quite tough, and so you really have to chew it a lot to break it down so you can get the maximum amount of nutrition out of it, and so molarization is essential. Now, the increase in body size is also related to the change in the environment. So once again, if you're in a forest, being too big is typically a bad thing. You get trapped. However, when you're on the plains and you're exposed, you have a couple of possible options. Either you can run away from something that's trying to eat you, or you can be bigger than the thing that's trying to eat you. And so what we see camels choosing the main option of becoming larger. So if anything's going to try and eat them, it's really going to have to work for it. So they're just naturally scarier, and so they're less likely to be preyed upon. Your average predator would then typically go for a smaller, weaker opponent rather than going after the camel. So North American camels display a range of forms, including giraffe-like camels with long necks, lightly built gazelle-like camels, and giant camels that stood about 3.5 meters at the shoulder. Now, most camel evolution took place in North America. However, in the Pliocene, we begin to see them migrating into Asia and South America. In North America, the camels died out in the Pleistocene, so during the Ice Age. Another group of interest are the Bovidae, and this is the group that includes cattle, bison, sheep, goats, antelope, and impala. Now, they don't appear until the Miocene, and they only begin to diversify in the Pliocene, so they're actually quite a late developing group. They are dominantly found on the northern continents, primarily North America, with some examples in Europe and Asia. In the modern world, they are now dominantly located in Africa and Asia, although North America does have some examples like bighorn sheep and mountain goats. Now, when it comes to North America, arguably the most prominent of the Bovidae were the bison and the pronghorns, and these both formed very large herds which would migrate across the plains of the central US. Now, in the case of the pronghorns, we can actually see from the fossil record that they began to become extinct in large numbers when humans first arrived in North America. Now, to be clear, they are still around now, but there was an extinction event driven by the arrival of humans where several species of pronghorns became extinct. In the case of the bison actually did extremely well in North America until the 19th century. The decrease in bison numbers experienced during the 19th century is primarily the result of the westward migration of European settlers during the expansion of the United States. So the overhunting of the bison that occurred is the result of both hunting for food, obviously the settlers needed something to eat as they were migrating westwards, but it was also a geopolitical technique. So by killing off large numbers of bison, it helped to limit the range and power of the indigenous plains people who were already there. And of course these are groups that relied on bison as a significant resource, so by reducing the number of bison substantially, it helped to weaken these populations. Now, once the migration had occurred, the bison were still extensively hunted, but this was actually for their skeletons. So once killed, the meat would be stripped off the carcass and the skeleton would then be ground down for fertilizer. So what you can see is during the 19th century there was an extensive pattern of overhunting of the bison that led to their population absolutely crashing. You'll be happy to hear that modern attempts to increase the numbers of North American bison have proven successful, and their population is no longer on the endangered species list. Now, many Artiodactyla are ruminants, which means they're cud-chewing animals with 3 or 4 stomachs. Now, these additional stomachs allow the vegetation which these animals ingest to be digested multiple times, leading to maximum nutrient extraction. So by passing the vegetable matter, the plant matter, between stomachs numerous times allows it to be exposed to acids for longer periods of time, allowing the food to be broken down more effectively, so by the time it makes it into the intestine, you can get maximum nutrient extraction. Now, this may well be a contributing factor behind the Artiodactyla becoming dominant over the Perissodactyla. So the Perissodactyla actually only have a single stomach. And in order to extract the maximum amount of nutrients from the plant matter that they ingest, they rely on an extended intestine in order to try and get the maximum amount of nutritional value out of it. However, this just isn't as effective as the multiple stomachs which are used by the ruminant Artiodactyla. So if we look at this figure, we can see a generalized diagram showing the evolution of the Artiodactyla. So of course down at the bottom here we have the common ancestor in the form of Diacodexis, and then we have one limb that comes over here to the left, and this gives rise to the ruminants. So of course these are all herbivores, and this includes animals like the deer, the bovids, the giraffes and the camels. Now you'll also see that we have another lineage here that gives rise to the Oreodonts, and then we have another branch that comes off over here to the right, and this gives rise to groups including the pigs and the hippos. Now the interesting thing about this particular branch is that the animals along here aren't exclusively herbivores. There's also some omnivores mixed in there as well. So I'm sure you probably know that pigs will eat both plant matter and meat, but it's a little known fact that hippos will also eat meat on occasions. So now let's move on to the Perissodactyla. Now, the common ancestor of the Perissodactyla appeared in the Paleocene, and diversification continued through the Eocene. So by the Eocene we have the establishment of the major groups, which includes animals like the horses, the rhinos, the tapirs, the chalicotheres and the titanotheres, and they become further distinct and established as we move from the Eocene into the Oligocene. The point of greatest diversity for the Perissodactyla is achieved during the Oligocene, and from that point on there's been a strong decline in the number of Perissodactyla species. Now, arguably the most diverse group of Perissodactyla are the horses. So horses are especially common in North America, where a significant portion of their evolution took place. Their high abundance means that the fossil record is extremely good, and so we have a pretty decent idea of the processes behind horse evolution. The earliest member of the horse family tree is a 20 to 35 centimeter high organism called Chalicotherium. It weighed about 20 kilograms, it would have primarily lived in forested environments, and it would have been a browser. Now, if we look up here, we can actually see the Perissodactyla family tree. So you can see we have this lineage coming up here, and this gives rise to the horses. We have this lineage coming up here, this gives rise to the tapirs, and we have this lineage over here on the right that eventually gives rise to the rhinoceroses. Now, if we look over here, we have another lineage that gives rise to a group called the titanotheres. Now, Chalicotherium actually sits right down here at the bottom, and it's actually a common ancestor for both the horse line and the Titanother line. So, as mentioned, Hyracotherium was a forest-dwelling animal, and it had a four-toed forefoot and a three-toed hindfoot, and each toe possessed its own small hoof. So if we look down here in this diagram, we can see Hyracotherium down here at the bottom, and this shows you essentially the forelimb. You can see it has four toes, and each of these toes would have ended in its own individual small hoof. Now, this doesn't sound particularly horse-like, however, the very good fossil record that we have for horses conclusively shows that Hyracotherium are related to modern horses and that they sit at the base of the horse family tree. Now, obviously, as we can see, to get from Hyracotherium to modern day horses, you can see we have several intermediate steps, and we can see over time the number of digits decreases from 4 to 3. Essentially, then the digits 2 and 4 here becomes more vestigial, and then by the time we're here, we simply have a single digit leg. So we have just the third digit left over, and of course it has its own very overdeveloped large hoof at the end of the leg. Now, in the late Eocene to early Oligocene, we see the horses split into two distinct branches. The two groups that developed are the three-toed browsing horses, which are now all extinct, and the three-toed grazing horses, which will eventually evolve to give rise to the one-toed horse with which we are all familiar. So the development of cement-covered, abrasion-resistant, high-crowned teeth by the horses coincides with the spread of grasses during the Miocene. So if we look over here, we can see a diagram that summarises horse evolution. So down here at the bottom we have Hyracotherium, and then coming off Hyracotherium we have two lineages. One's coming up here, and that's going to give rise to the horses, and the other lineage is coming over here, and that's going to give rise to a group called the Paleotheres, and they're eventually going to evolve into a group called the Titanotheres. Now, horse evolution, as you can see, during the Eocene and the Oligocene is dominated by the browsing horses. So these are horses which are going to primarily live in forested areas, and they're going to have a diet which is dominated by leaves, twigs, shoots and berries. Now, as we transition from the Eocene to the Oligocene, we know there is a change in climate, and this leads to the large forests of the Eocene and Oligocene slowly dying back, and they are replaced by grasslands. And so towards the end of the Oligocene and into the early Miocene, we can see a noticeable shift in horse evolution. We can see the rise of the three-toed grazing horses in this green region, and eventually we have the demise of the three-toed browsing horses by the late Miocene. So as we can see, the three-toed grazing horses obviously move out into these extensive grasslands and they prosper. The vast majority of evolution takes place in North America, and then as we move into the Paleocene and the Quaternary, we can see that the horses spread out into the Old World, so obviously they go into Asia, Europe and Africa, and then we have some groups that move south into South America. Now, horses develop an escape strategy based on speed, so once they're on the plains and they're exposed, hiding behind trees and bushes isn't going to work anymore. So we tend to see horses getting larger, so they're more imposing and therefore less likely to be attacked, but we also see them developing a strategy that involves being able to run away very, very fast from the thing that's trying to eat you. This escape strategy is reflected in the increase in leg length that we see with horses and the move to a single-toed foot. And so it's primarily the increase in leg length that's important, because of course that's going to increase the step of the horse, meaning that it can cover larger distances in smaller amounts of time. So it's going to be able to run away from the predator more efficiently, and so it has a higher chance of being able to survive. The other surviving Perissodactyla group, so that's the rhinoceroses and the tapirs, increased in size from their early Cenozoic ancestors. So this increase in size and diversity occurred throughout the Eocene and into the Oligocene, but from that point on there's been a steady decrease in the number of species of both the rhinoceroses and the tapirs. Now, most of their evolution occurred in the Old World, so that's Africa, Europe and Asia, but North American examples were present until the Pleistocene. So at 5 metres high and 13 to 14 tonnes, the largest land mammal to have existed was actually a hornless rhinoceros. So if we come over here and look at this diagram on the right, you can see some diagrams showing you the different sizes of modern rhinoceros and this truly massive hornless rhinoceros here in the dark grey. So you can see in green we have the Sumatran rhinoceros, in yellow we have the black rhino, in red we have the white rhinoceros, and in blue we have the Indian rhinoceros. So these are the rhinoceros species with which we would be familiar with. In the light grey we have the woolly rhinoceros, which was of course present in the Pleistocene, so during the Ice Age, and then behind that we have this hornless rhinoceros, which is called Perissodactyla, and as you can quite clearly see, it was a real monster. The two remaining groups of Perissodactyla, which are both now extinct, are the chalicotheres and the titanotheres, and both of these groups steadily increase in size throughout the early to middle Cenozoic. So the titanotheres have a good fossil record, but they only existed in the Eocene, making them arguably the shortest lived member of the Perissodactyla family. Now, during this time frame, though, they did undergo very, very rapid evolution. So initially they started off as quite small forest-dwelling browsers, but by the time they make it into the later Eocene, they've evolved into rhinoceros-sized grazers, which are living on open grasslands. So they reached a maximum height of about 2.5 meters, and they developed a nose horn that became more pronounced as their evolution proceeded. So the next group are the chalicotheres, and the chalicotheres have a relatively sparse fossil record suggesting they were somewhat solitary creatures, so chances are they didn't form herds. The largest member of the chalicotheres reached a size equivalent to a very, very large horse. Now, we know they first evolved in the Eocene and they make it all the way through to the Pleistocene, so the Ice Age. Initially they began evolving in Asia, and by the Eocene they've managed to migrate into North America, and they do very, very well in that environment. So North America at the time, of course, in the Eocene and into the Oligocene, is covered in extensive forests, and we see the chalicotheres adapting to that environment, and they split into two broad groups. The first group develops long necks and very long tongues, a bit like a giraffe, which they can use to essentially lift their head to great heights and pull branches down to remove leaves. The second group, which we can see in a picture behind here, develops very large forelimbs, and at the end of these forelimbs it has claws rather than hooves, and this allows it to use its arms to pull down branches so that the teeth can then be used to pick the leaves off the branches. Now, this is an interesting adaptation when compared to the other members of the ungulates, all of which have hooves. So this makes the chalicotheres a very distinctive group in their own right. Now, the chalicotheres begin to suffer as we have the dying back of these large Oligocene forests, so by the time we're in the Miocene, the chalicotheres are in full retreat, and so by the Miocene they're pretty much gone from North America, they're gone from Asia, and they're just hanging on in Africa, and they managed to make it through till about 700,000 years ago, living in Africa, but steadily they are outcompeted by other forest-dwelling organisms, including the primates, and eventually, unfortunately, that's it for them. So this is a good place to stop part 3, so please stop the presentation, get up, have a walk around, go and get a glass of water, take 5 or 10 minutes to relax, and then please come back for part 4.